My name is Pranav Devalapalli, and this is my Physics 2212 Lab 5 report. So the purpose of this lab was to observe Faraday's law physically and also model it through a simulation, after which we would compare the two results to see how it varies. Some fundamental concepts and models used were Faraday's law, which is the first equation shown on the right, the formula for magnetic flux, which is the second formula on the right, and Lenz's law, which essentially states that the induced current will generate a field that opposes the change in the magnetic field. For a visual representation of Lenz's law, here's a diagram that demonstrates the bar magnet that we will do an experiment on. The bar magnet falls through the aluminum tube and generates a magnetic field which increases downward, as denoted by the red arrow. This means that by Lenz's law, the green arrow is the field generated by the induced current, and that must oppose the red arrow B field. By using right-hand rule, we can put our thumb in the direction of the opposing field and use the rest of our fingers to see the direction of the induced current, which in this case is counterclockwise from top view. So the method for this experiment was to first find the north end of a bar magnet using a magnetometer in a phone, after which you would take the bar magnet with a known dipole moment, for this specific case 2.959, which we calculated from the third lab, and drop it through an aluminum foil tube of a diameter of 1.5 inches with an inner diameter of 1 inch. And after doing this 5 times, you record the time to see how it falls through the tube, and then record and analyze the data accordingly. A quick preview of the result is that the average time for the physical model was 1.326 seconds, while the computer simulation showed around 1.374 seconds. So in this experiment, the system is the bar magnet in the aluminum tube, and the surroundings is everything else. Some assumptions and initial conditions that needed to be made were that there is no friction between the magnet and the tube due to unintentional contact, and that there are no external magnetic fields present, that the magnetometer is accurate in the first place. And from this, we can deduce that the average time for falling was 1.326 seconds from the experiment. So here's the glow script code that was used for the computational model. The first part right here demonstrates the geometry of the tube, and the measurements here were modified accordingly. Sorry. This part is what creates the tube in the simulation in the first place. This part does the properties of the magnet, and this is the magnet in the simulation itself, which sets initial values for the velocity and the time. The dipole function is here for the magnetic dipole, and this is for the d flux over dt. And then this part calculates the gravitational force, and that this whole function is actually the magnetic force. And this last part is the final statements that bring all the code together, which displays everything that we need to see. So this is the final output from the simulation, which, as you can see, it gives us a graph and a final time of 1.374 seconds. So to compare, the physical experiment gave us a time of 1.326 seconds, whereas the GlowScript simulation gave us 1.374 seconds, which gives us a percent error of about 3.62%. So to interpret the simulation, red demonstrated a clockwise and blue demonstrated a counterclockwise current. And if the magnet were flipped, both the field and the opposing field would also be flipped. So the induced current would be changed to the opposite direction. But with all this, the magnet would still slow down as it falls through the tube. The total in-tube time was slightly less than the time from the computational model. So to fix this in the computational model, the assumptions that we made earlier, if we were to eliminate those, it may make if we were to account for those, sorry, it may make the computational model more efficient and accurate. And the velocity graph was shown to be perfectly horizontal, as you can see here, which implies a slope of 0, which is an acceleration of 0, which is equal to a net force of 0 by Newton's second law. Some sources of error may be that the time may not have been perfectly measured, and that other measurements like size of the magnet in the tube may also not have been exact. For the what if and why questions, if the resistivity of the conductor were reduced as close as possible to 0, by Ohm's law, R would decrease, so then I would increase because R is in the denominator. So that means the opposing field would be greater due to the current being greater, which means the magnet would fall slower. If holes and slots were cut into the tube, this would result in a less upward magnetic force, resulting in the magnet having less opposition, enabling it to fall faster. Thank you.